Happy Tuesday, everybody. This is 2 days after the long Thanksgiving break where we were off Zoom, and now we're back on. But today is actually a wonderful seminar for the Mechanical Engineering Department. We have our distinguished alumni with us today. I'm pleased to introduce to you guys Krishna Nadella from one of our alum. Krishna did his undergraduate degree at Bangalore University of India, and then he came over here to UW where he did his master's and PhD working with Professor Vipin Kumar. At that time, Krishna became bitten, I would say, by the entrepreneur bug. He'll talk about this, I imagine, but he's been a serial entrepreneur with technologies. He was a founder of Microgreen. There was also the founder of is it Alua, did I pronounce that right?
Yeah, Ayuwa.
And now he's now on a new venture that he'll talk a little bit about as well. Krishna has been a strong supporter of our department, and we've also been very happy to have him as well. He was a College of Engineering Diamond Award winner in 2011, and he's also been helping our department with some of our teaching as well. And so he's also been an instructor in our classes. So I think for Krishna, he's done both the academic with dozens of papers as well as many patents as well. But we look forward to your talk today for us. Just as a reminder for everybody, we'll do the Q&A session at the end, so Krishna will present. So if you have any questions during the talk, I would encourage you guys to use the chat feature to ask your questions, and then we can field those questions at the end. And otherwise, I think I'll let Krishna begin his presentation.
Thanks, Nate. Hello, audience. Like Professor Nadella said, I'm a graduate of the Mechanical Engineering Department. I've been associated with UW since the day I landed in America about 21 years ago. I got my master's and PhD here. And I came to the US to learn manufacturing and go back home to India to build a manufacturing business. And I'm still trying to do that. It's just 21 years later, because there's so much interesting tech here that can be commercialized in the US itself. I've been essentially working to do that. So what I'd like to talk to the audience today is about these lessons that me and my team kind of gleaned over 2 decades of commercializing an advanced materials technology from the University of Washington. And anyone who's kind of familiar with startups or entrepreneurship will kind of look at this and say, why did it take 20 years? Why is it a 2-decade effort? And in fact, I've been answering those questions myself. And I'd like to share some of the answers to these questions that come up on why it takes this long. What do you find on the pathway when you're trying to commercialize technologies like these from university environments? And I hope to leave the audience with a few takeaways that they could use if they're attempting to do something similar, with the idea that you're going to make different mistakes than I did. Right? We don't have the time in the world to make all the same mistakes. There's no need to do the same thing and relearn the same lessons. So hopefully anyone who's looking at this and starting their own advanced materials venture is looking at new mistakes and will share with that with the audience in the future. With that, I'll get started. So the commercialization team, Professor Vipin Kumar is the inventor. He came up with a lot of the technologies that we primarily are focused on commercializing through my work in the world outside the university. And I always saw myself as an entrepreneur, and my education is really focused or is in the benefit or as a foundation for entrepreneurship, if you will. So when I went into the PhD program, my specific focus was manufacturing and design and how to use that in new materials to go out. Professor Kumar really laid the foundation for this technology by inventing this industrial scale process to make microcellular plastics. A lot of industry interest was generated thanks to the Cellular Composites Consortium he ran in the 90s, well before I showed up at his door at the University of Washington. The work during that consortium led to this key patent, the 055 US patent on the semi-continuous process that led to this Thomas Edison Patent Award. We then were given a DuPont Packaging Award for cost and waste reduction in plastics technologies. And all of this work basically resulted in Professor Kumar and I working together, each of us getting about 40 patents on our way there. So with that, and one of the key partner in this effort has been the UW Co-Motion Office over the years, working very closely with us, helping us make this effort a reality. Without Co-Motion support, it's really hard for a startup company as is in the world, but having Co-Motion as a partner has really helped us move forward. Very quickly, I want to go through for the first half of the presentation, what we did, what we did in my previous entrepreneurial efforts, what the results were at a really big picture level. And then the next half of the 30-minute presentation, I'll focus on the lessons and leave about 10 to 15 minutes for questions. So please type up your questions into the chat as we go along. So the basic technology we are trying to commercialize was invented in MIT in 1984, right about the time Professor Kumar was showing up to get his PhD or join the PhD program at MIT. It is called solid state microcellular plastics. Essentially, the plastics industry went to Professor Nam Su in MIT and asked the simple question: we want to reduce the amount of raw material used in a thin wall package. Turns out in the packaging world, what you need is stiffness as a primary functional attribute, not strength, right? So there is way too much plastic in a thin wall packaging material where stiffness is important. So you have to somehow create a very high stiffness, low weight material. That's essentially the technical problem. So the technique by which they were able to create in a 1 millimeter thickness, somewhere between 100 to 1,000 bubbles in order to reduce the weight, was to use this three-step process. In the first step, there's a pressure vessel. We put a solid plastic, typically an extruded piece of plastic, into this pressure vessel, expose it to high pressure carbon dioxide gas, and the plastic absorbs the gas in the environment into itself, slowly increasing the weight. You're typically absorbing somewhere in the 1 to 7% by weight of this plastic is absorbed in the form of CO2 gas. Now, when you take this material out of the first step, you have a supersaturated sample that is sitting in the atmospheric pressure and atmospheric temperature. And this thermodynamic instability that comes from supersaturation, if you simply provide it energy by heating it in a hot water bath, somewhere close to 90 centigrade, you will see that the volume of the plastic expands because there are billions of small bubbles that are created. Typically in the thermoplastics that we work in Professor Kumar's lab with, we can control in a cubic centimeter anywhere between 100 million to 1 trillion bubbles per cubic centimeter. And typically the temperature in this heated bath is somewhere close to the glass transition temperature of the thermoplastic material. So as you can see, it's a batch process. But what is very unique about this technology is that this batch process, nowhere in this technology is the material melted. It's always in the solid state. And this remaining in the solid state, using the strength of a material when it is in the solid state, is enabling us to make microcellular bubbles in there. In fact, Professor Kumar is far away from microcellular. He's into the 1 to 10 nanometer bubble size in his lab at this time. But what we were commercializing is microcellular plastics. So this is the 1980s. By the end of this decade, Professor Kumar had done work with many of his colleagues in the labs at MIT on polystyrene nitrogen and so on. And when he came to University of Washington, there was one clear mandate. How do we industrialize this process? And he kind of dedicated his research group to industrial process design for this very unique process technology. So again, the goal is to get to a certain material composition, which is in a thermoplastic material, you want X number of bubbles per cubic centimeter. In order to get to that material composition, a new process was invented. We'll go through this again and again, that what is important in this step. In the 1990s, when the consortium started in the mechanical engineering department, over 3-4 years, all the focus was on the specific plastic called polyethylene terephthalate, PET. All of you know it. It is the plastic that carbonated. So soft drinks like Coke and Pepsi are sold in. All the water bottle plastic is the same PET. And because it is ubiquitously used and it is the world's most recycled plastic, there's a lot of interest in reducing the weight per unit area or the density in PET. Turns out the other big problem with PET is the traditional techniques to make bubbles by liquid state processing the material don't work like in polystyrene. So there was a real need to develop a new technique which would make bubbles very reliably in PET. With that focus, Professor Kumar essentially invented this technology called the semi-continuous process, in which a roll of extruded PET is interwoven with a roll of paper towel. So you have a layer of PET, a layer of paper towel, and this interleaved roll is then placed in a pressure vessel and is injected with CO2 gas. And then the process is essentially similar. You get some CO2 gas somewhere between 1 to 7% by weight in, and then you remove the roll and unwind it through a heated liquid bath followed by a chilled bath. And the paper towel is recollected so you can reuse it in the reuse it again and again. So the key aspects here are this process of interleaving, right? This is a new step again. This process of saturating a roll is a new step. This thing about heating the material in a liquid bath at industrial scale is a new step. All of this was proven at a bench scale. Now the goal is how do we take this into the industrial world? That's where I came into the lab in 2000, saw this technology sitting around, saw what kind of beautiful materials it was creating with these incredible properties, and couldn't believe my luck that I would have the chance to take it out to the world. And I was celebrating too soon, as you will see very quickly through the presentation. So what happens when you apply this this technology, the semi-continuous process technology, to recycle PET, which is PET made from post-consumer recycled bottles, right? What happens is it enables reduction in the amount of plastic used per application by about 50%. You can use 50% less weight of plastic to achieve the same application needs. So imagine a coffee cup. Instead of having 8 grams of material in a cup, you could do the same job with 4 grams of material. And because the bubbles are so small, in many cases, they're smaller than the critical crack propagation radius, you find that the material is unbreakable. I mean, you can continuously try to break it with your hand, it won't break. You'll find that because of the bubbles, the material is more insulating than what materials are out there. So this better performance with less material gives you a low cost advantage. And because we're only using CO2 gas, you can preserve the recyclability because the chemistry of the plastic is not changing in any way, right? So what you're seeing is here is the raw material roll extruded going into the process. And what comes out is an opaque, bright white material with twice the area and the same weight. And that whiteness is coming from all the light that is getting reflected back because the bubbles are acting like prisms. It's very hard for us to make anything less than 90% brightness. The paper industry, in order to get to the same brightness, uses a lot of chlorine to bleach the paper to that kind of whiteness, right? So you can see kind of the benefits right there. So very high quality appearance, superior printability, very high toughness and crack resistance, high stiffness to weight ratio, which is the original goal, good insulating properties. We can tune the service temperature range by just using CO2 gas to crystallize the material. So the service temperature of PET, which is typically not more than 60 centigrade, can be increased all the way up to 220 C in some cases. And then tunable gas barrier properties for oxygen barriers, specifically for shelf-stable foods, is a really important property, right? Ideally, what we should be replacing is opaque solid plastics like high-impact polystyrene and paper, which is, despite its image of being a very environmentally friendly material, in reality uses a lot of energy and releases a lot of greenhouse gases during its manufacture. So when you look at the key invisible attribute in this material, we have this optimized microstructure for individual applications. So here is a good example of what a coffee cup looks like: a 25 micrometer skin followed by very small bubbles, followed by very large bubbles in the middle, and repeating the structure on the other side. This structure is optimized for insulation and stiffness. So the density is reducing in a gradient manner through the thickness. And with any mechanics calculations, you will very quickly see this is what is optimized. Stiffness is achieved by gradient density reduction, unlike in an I-beam or other step change in density between the skin and the core. Right? The key visible attribute is it has brilliant surface and very high-end aesthetics. People, when they touch the material, they think it is either solid plastic or some very special design paper to give that kind of finish. So achieving this composites functionality in a thin wall mono material. So the material started as a thin solid material, and we are creating these multiple layers on the inside without any lamination. All these layers are essentially integrated together just through the process technology, right? And another key attribute is this ability to manipulate the microstructure in thin walls. In a 1 millimeter thickness, here is optimized for coffee cup. Here is optimized for a paper industry application where we are trying to replace paper, right? Process it in the paper making equipment, but the goal is to make sure that the surface has a matte finish and there is no reflection of light on the surface. They're making the bubbles just enough so the surface is not flat, and then moving the small bubbles on the inside makes this feel like a specialty paper. People can't tell the difference. So this is the key foundation that Professor Kumar had established while we were going out. So the framework that we should all be remembering as advanced materials practitioners, going into this lesson, going out to the world to commercialize, is this basic division that I see in my head, which is typically the primary innovation in an academic lab in advanced materials happens in the material composition. And in order to achieve the material composition, typically there may be a brand new method, like in the case of Professor Kumar, or there may be a modification of the existing method, right? So the process technology is not the key focus. It is just a vehicle to achieve the material composition. Similarly, when you have a brand new method or modified an existing method to get to this new innovation in material composition, you may need a new design of equipment or modify the existing design of equipment. And sometimes, if we're lucky, it is just new tooling designs are enough, right? But all of this really kind of gels together or is distilled only when we choose a proper end-use application for this material composition, right? And we also not just choose the end-use application. For example, in this case, it's not just packaging. The minimum viable product we had to choose was a airline coffee cup in the packaging industry, is when all the lessons or all the efforts to get to this end application with that material composition will much closely define what the process and equipment are. So it's very important to be able to choose the right MVP in the right end-use application to make sure this happens. It's also very important, and you'll all face this challenge, is there's a lot of pressure, especially when you're commercializing, to patent constantly, right? And you'll very quickly find out that process and equipment patents, as good they are from teaching the world how to do stuff, they really offer very little protection in my view, simply because you can't go into someone else's factory to see what process they're using or what equipment they're using. My suggestion is that you should focus all your resources, all time and money, for intellectual property protection on material composition and end-use applications, and ideally either teach away the process in journal papers or so on, or keep them as trade secrets, both the process and equipment. I think it'll save a lot of financing, equity financing capital, and a lot of grief trying to get patents for process and equipment. So Microgreen Polymers is the first company I started right after my master's with a colleague who also got his master's from Professor Kumar's lab, Greg Branch. Both of us kind of went into it. Greg was fully dedicated to it, spent many years trying to build it. We started out with an exclusive license from the University of Washington for all technologies out of Professor Kumar's lab for all fields of use. And we believed this was important, and so did the University of Washington believe that it is important for investors to be able to support our work to have this exclusive license. I want to make this key point. This all fields of use may not be necessary by showing you the negative aspects of all-encompassing exclusive license. We then went out and got $1.5 million in state and federal grants over the time period from 2002 to 2014 to support R&D. We raised about $80 million in equity and debt, grew the team to 163 employees by the third quarter of 2014 because of the growing product demand. And essentially, our efforts led to commercializing the solid-state microcellular PET. We went through 3 iterations of technology development at a global 30,000-foot viewpoint, and essentially won numerous industry awards for innovation and sustainability. Many applications and markets were attempted: printing substrates, hot beverage coffee cup, heat resistant to 120C, a dual ovenable tray, heat resistant to 220C. Enjoyed a lot of commercial and strategic interest from large companies in the material space, commercial orders from airlines, hotels, and so on. Things were going really well from a technical development, product development standpoint, but there were a bunch of challenges that seem very small in the moment that very quickly become large. Despite all this apparent success, Microgreen ended up being dissolved via foreclosure and auction process in 2015. A large industry player bought the company's assets for $2.5 million. And essentially the company failed due to 2 critical mistakes. One of them was underwriting significant capital investments with commercial deals that were not financially viable at the orders we had in hand. Again, this is a key idea. You have a certain amount of orders in hand. What is the size of the equipment you're putting in place? And this large with production line, I'll make my point much better in the future once you understand this, that you have to be very careful of what size capital investments you're making to the size of the orders you're getting. And then the size of the orders you're getting typically depends on the market adoption rate, which is not very easy to figure out when you start first your commercialization process. Then the second big problem we had is we raised capital at the end from an investor whose investment goals were misaligned with the company's needs and risks, right? So when you're growing that fast and essentially investors want to support you, typically even then it is very important to slow down and look at the alignment of what investors' goals are for their money and what your company can actually deliver with the attendant risk, right? No one assumes that you will fail, but what happens if you slow down? What happens if a problem that you didn't anticipate comes up? Will the investors' investment goals still be met? We essentially made an error there, choosing to accept investment from someone whose goals were misaligned with us. So that happened, and Microgreen closed in 2014. For anyone who's interested, you're welcome to see this video you're welcome to read this newspaper article in Everett Herald, which explains a little better what was happening within the company. So the product vision in 2002 is Greg and I were thinking through what to commercialize this new technology in. And lo and behold, we're in the world of Starbucks here in Seattle. And all consumers in Starbucks were faced with this choice. You drink this coffee, and then out of the store as you're walking out, you have a choice of 3 bins. And you're going to throw the cup in the landfill because the cup has a polyethylene coating on the inside of this paper cup in order to make it leak proof. You have this polystyrene lid, which is now largely changed over to polypropylene that goes into the recycle bin. And then this insulating sleeve, a cardboard sleeve on this that goes onto this truncated cone, which this cup is, can either go into the compost bin or it can go into the recycle bin, right? But you have these 3 choices. And then our vision was, hey, how about a cup and a lid that just goes into the recycling bin? And the cup is made from recycled PET. A very simple vision to explain the benefits of the technology without having to go deeply into the science. Make insulating coffee cups from recycled water bottles. That's essentially the tagline, if you will, which enabled us to raise or get a bunch of support from investors. This is a great graphic that from Professor Kumar that I borrowed, taking recycled PET and adding CO2 to get to these coffee cups. Alaska Airlines was our first customer in 2012. So now let's jump in deeper into the actual process technology, what was going on. So the pilot process, right, that we scaled up basically has this interleaved roll, and we put it in a pressure vessel. And very quickly, we found out that you can't use water baths to foam anything in the industrial world. Because it was a new manufacturing process and needed a new equipment design, we went into this iterative equipment design. So we eventually found this paper industry standard machine called a flotation air oven, which works extremely well to make this material expand in volume. A water bath and so on don't work very well. An infrared, that is oven that's used in the plastics industry, doesn't work well. We can go deeper into why at a later time. So at the end of 2010, we were doing all this work in Green Bay, Wisconsin on borrowed equipment, rented equipment, and so on. And there was a key question of which downstream converting process will we use in order to go make these coffee cups. So the first commercial process where we set up a production line in Arlington was essentially using the same thing. And what we did is at the end of a flotation air oven, we put a paper industry standard machine called a sheeting machine. All it does is it takes rolls of material and it sheets it to make sheets of material, 28 inch by 40, 4 foot by 8 foot sheets of 1 millimeter thick materials, if you will. So we had to couple these things for various technical reasons. So standard machines from the paper industry that were coupled together in a process technology. There's a real problem in this coupling process, right? I took Professor Kumar's axiomatic design course where he tells me not to couple, and I still did it. And it was not fun. So why were we making flat microcellular PET sheets? Because with this, the goal was to sell to downstream industry, right? Roll interleaving, roll saturation, coupled roll expansion and sheeting. So this coupled operation of the standard machines is a modified process method. Why were we doing it? Because then we could sell the material into the paper industry that currently sells paper rolls. And the downstream converters typically print and cut a blank of material like that in the shape of a fan and wrap it around a mandrel and then punch out a bottom and then put the bottom at the bottom of this truncated cone and make a paper cup. That's why. So we attempted to do that. And here is one R&D example of a microcellular PET cup. It looks beautiful, but at the bottom, we had some real challenges. And these challenges needed us to modify standard downstream convolute forming machines. The challenge is we could not go down this route because there was no clear pathway to making the material heat resistance for a coffee cup. So again, our product vision was built around a coffee cup, and hence we could not use this technique of making cups to go after a coffee cup, right? Or at least the success was not guaranteed. If it was an ice cream cup, this would have been a good choice to go and make the modifications on convolute forming machines. But by choosing a coffee cup, we kind of limited ourselves to not being able to use convolute machines. Then the second iteration of the commercialized process started, where we said, okay, we can't use that. So let's merge a standard plastics industry thermoforming machine, right, with an air oven. Again, we are coupling, instead of a sheeting line, a thermoforming line. And in this case, it was necessary to couple these two things together to be able to make a deep draw heat resistant cup. And the cups work very well. But the challenge again is it's a custom machine. It's not even two standard machines like in the sheet making that were attached together. This is a custom machines from ground up. The challenge with this custom air oven plus thermoforming machine combination is we had a very narrow process window for this custom process in this custom machine. And but the product worked. There was a clear pathway to make heat resistant material. We achieved heat resistant coffee cups, and the coffee cups, they were not 50% weight reduced as we expected. They were 41% res, but 2 times more insulating than a paper cup. So that part of it worked well. And essentially, we were able to launch this InCycle airline coffee cup into the industry. A bunch of large airline customers adopted it, and we had a 1 million cups per day production rate by the end of 2014. Um, uh, and this line here, just remember, is 60 inches wide, right? And now in iteration 3, by early 2015, Microbean had developed more standard operating thing where we would go from a roll to a roll of machines, and then we just go to standard thermoforming machines without any customization. So that happened in early 2015. So what you will see in these lessons, I will try to derive them, is to commercialize successfully in a lean startup by Eric Ries, you typically listen to this thing about value hypothesis and growth hypothesis. In value hypothesis, you're trying to prove that your innovation and product is valuable to potential customers. So again, the innovation is material composition, and the end use application together have to be valuable to potential customers. Typically, it's easy to meet this because when you get federal grants for your R&D and so on, there's a lot of peer review and merit review processes that kind of give you an inkling that this is in fact valuable. So it's relatively easy to meet the value hypothesis question for academic researchers in advanced materials. The real challenge is growth hypothesis. In the growth hypothesis, you essentially are trying to tell people, okay, I make this product, it is valuable to customers, but how will every new customer discover this product in innovation? And that is where the money is in the growth hypothesis. What you'll very quickly find is, in order to go from the value to the growth hypothesis, the advanced materials, you have to scale up the innovation to build that minimum viable product. And the real challenge is to build it with the investment that is sufficient to get to minimum viable revenue capacity, which means you can't just say, we will build it, they will come, which is what we did at Microbean, right? We had a capacity of 1.5 million cups per day, but the production orders were for 500,000 cups per day. So we overbuilt capacity. It's not very easy to find out what is the right capacity to build. It is because even after the customers discover your innovation and they buy at a certain rate, the key question is, at what rate will the market adopt your innovation is not very clear, and it is very hard in advanced materials to figure out. And this market adoption rate is what will tell you is the capacity you should build. And then you say, if this is the capacity that the market will buy at, what should my machines look like? How big of a company should I build? How many employees should there be? So on and so forth. So those are the key challenges that you'll quickly find. So you need, these are constantly in tension. What market rate, what is the market adoption rate? You don't know this until you scaled up this whole thing. So to go from here to here was $12 million in Microbean. And then when we found out that the convolute cup won't get to heat resistance, then we had to invest another 20 to 25 million to get to a hot cup. So just this step is about $35 million, right? And after that is when you discover the market adoption rate. So what are the lessons I learned from this that I'm sharing with you, and I'm actually trying to implement them right now in Vesicus? The first lesson is, before you begin, you should seek to both read existing literature and listen to people who have done it in the past. So I was pleasantly surprised, just like in our science-based, engineering-based research, there is a whole body of research in innovation management, policy, and so on. And these articles are really good articles that talk about the challenges in commercializing new manufacturing processes, new materials, and so on. I highly recommend reading it, especially this Beating the System PhD thesis from MIT. And this particular report from McKinsey & Company were very useful. So it's important to not only read these kinds of articles before you get started, but it's also important to seek out mentors who have attempted material commercialization before. I learned this really too late in the game at Microbean, but I would, if I were doing it again, which I'm doing now, I would seek out both startup veterans who've attempted to do this before, succeeded or failed, doesn't matter as much as that they've had the experience. And more importantly, getting retirees from large companies like DuPont and Corning is very important to get on, because many people with that kind of a background, new product commercialization from large materials companies, they have something to still teach the world and are happy to engage if given the opportunity. Lesson 2, right? What is the most important lesson I would take away? Material commercialization is a long haul period. There is no way to just make it 18 months just because you have a new pot of money from investors. So here is a source from McKinsey and Company. In pharmaceutical, this is the typical evolution to revenue peak. In aerospace, every time a new plane is launched, you see that significant sales after a new launch, then there's a lull, and then there's a rebound when the plane is extended or new efficiencies come in play. The trouble in materials and chemicals is after product launch in microgreen, this is 2010. It just is a long haul to get to any major revenue. And here is an example of that. PVC pipe was introduced in America in 1952, primarily for chemical plants and pickle factories. Then all the way till 1965, PVC could not get any kind of code approval because it faced heavy opposition from the people who are supposed to be using it at the end, the pipe fitters, plumbers unions, plumbing distributors, and so on, right? With this kind of a downstream supply chain pressure, the code approval battle took almost 13 years. And then when the Federal Housing Administration accepted it, that's when it started to launch. Right. So from 1952, if this was 2010 at Microgreen, right, this is almost 20 years later. This is somewhere in 2030, 2032 is when we will be gaining this kind of revenue for the commercialization effort if Microgreen were still alive. But right now our effort had broken down and we had to restart it. So we're drawing a new curve, if you will. So it took 15 years to reach reasonable volume. The third lesson, and this is a key lesson, and a lesson that I would repeat again and again, it is to focus on the primary innovation. The primary innovation in this case was making bubbles in PET. It was enough to simply sell that primary innovation because a lot of people would buy. What we got enamored with is our own end-use application idea of the coffee cup. And once we merged the coffee cup idea with the primary innovation of microcellular PET, there were all these secondary and tertiary innovations, new processes, new machines, new tooling, and it immediately dilutes the focus and it starts to really get in the way of execution, both at a sales level and at a manufacturing level. So again, these secondary and tertiary innovations depend on what end-use application you're choosing. But I would relentlessly focus on the primary innovation because just selling one differentiating factor that really is groundbreaking in a given industry is hard enough. Trying to layer on top of innovation, another innovation, it very quickly dilutes the amount of money and energy and time you have to achieve progress. The fourth lesson I would take away is you should choose to directly compete with only one entity in the value chain. First and foremost, you have to define the value chain. Who is upstream to you? Who is downstream to you clearly? Understand what the economic drivers are for each of them, and then choose only one entity to directly compete with. And for all the remaining entities in the supply chain, you have to seek out and collaborate. They may say, no, that's fine. Just get used to rejection anyways. But here's a good example. For the convolute formed cup, people buy rolls from a paper roll manufacturer who coats it with polyethylene. Then the downstream cup converter buys the roll, prints it, cuts the blanks, makes the cup, and gives it to the distributor who gets it to the customer consumer. And then the municipal recyclers have to deal with the material when the consumer throws it out. We sought to replace this by doing that step, doing this step, and doing that step. We are taking on too many fights in the supply chain. Everyone is going to resist change. So the right approach is to only focus on making rPET rolls and don't do anything upstream or downstream from us. Eventually, when the company is profitable, you will have the ability to do that, do this, and so on. At Microgreen, we try to boil the ocean by trying to do all these three things at the same time, for example. The fifth lesson is to choose the right product format. Almost always in every industry you're trying to commercialize in, there is a standard format in which the material is sold in the value chain of the end application. Is it a roll? Is it a sheet? Are they powders, bars, rods? What is that standard format? And what is the smallest dimension of the standard format that someone is making money and making a living and building a company on? So at Microgreen, when we chose to couple the machines together, we went away from a roll to a web. Basically, the input was a roll, but the output was not a roll. It was a finished shape, right? This choice, which is unusual in the industry, right? So some people do it, but it's not usual. You immediately took us away from a standard format of a roll. And then by choosing a 60-inch wide, 1500 millimeter machine, whereas the most smallest standard dimension machine is a 600 millimeter, 90% of the world market uses somewhere close to this metric. And these machines are less than 500,000 each. By going to an American size of 1500 millimeter with inline coupling, the investment very quickly went up to about $5 million, right? So if you were to just choose the standard dimension machine in the standard format for your industry, you'll save yourself a lot of grief by not over investing in capacity. It also enables you to serve small end use markets profitably. The lure of large end use markets is the wrong approach to go for an advanced materials company initially. Going after a very large application just because you need $1 billion total addressable market to attract a venture capitalist is the wrong way to go about doing it. The fifth lesson I have is to choose the right geography. The geography we live in and work in may not be the right one for the initial commercialization. It is best to choose a geography where the downstream players, right, people who would buy stuff from you are already seeking the innovation from you. For example, in our case, PET foam was already of a great interest to downstream players in all major European countries. In America, no one cared. Right? So it is better to choose a high GDP per capita economy in EU with a small population, because then what happens is the size of the investment per iteration is smaller. The size of the overall financial and reputational risk is much smaller. And most importantly, the number of naysayers who tell you will constantly fail, they're just fewer because of geographic fragmentation. I would also consider locating your operations in a low-cost geography to reduce both the risk and cost per iteration, especially geographies where your innovation is too early, because people won't care about stealing the innovation from you and doing something. So if I were to locate, say, early on in Morocco, for example, and went after the European market, I think you get the benefit of a very high price point in sales and a very low cost geography where people in Morocco are not caring about copying your innovation or so on, because it's too early for that market. The sixth lesson I have, and this is mainly for the academic audience here, is to choose partners with the right business model. Typically, many advanced materials technologies are innovative platforms. They have multiple applications in multiple industries. So it is important to choose a licensee or a commercialization partner to license to that focuses on one field of use. When Microgreen went and got all those fields of use as an exclusive license from the University of Washington, all of it done with good intentions, the trouble is the market forces the company to focus on only one field of use. That is all the time, money, and resources you have. The challenge is when the company had all those licenses, the negative thing that happened at the University of Washington was it really dried up sponsored research opportunities from industry for Professor Kumar, because every company would come say, we want to do some research, is the IP open? And then the IP is licensed to Microgreen, and they would go away. So I would rather choose to go after one field of use, and then once the first one gets some traction, there'll be multiple spin-outs or licensees that will develop later. I also think it's very important to choose a commercialization partner that commits to build, operate, or use your innovation, not one that improves the engineering or implements the engineering and then wants to sublicense. Because I personally don't believe that there is a business model in which is licensing, sub-licensing business model builds a startup company in advanced materials commercialization. You have to go do it and provide whatever end use application in the market, not just through a sub-licensing effort. The seventh lesson I have is right people on the right bus. You need at least 2 champions for each field of use. So in microcellular PET, Professor Kumar and I have been together. I've now recruited a bunch of more people following my own lesson of getting people from the startup and the advanced materials world. And these champions have to commit to patiently build over the long haul. If you're in this to make a Facebook kind of money in 18 months, it's not going to happen. And the other key personality trait is the ability to stay excited about the effort over long periods of time. You will only find those people when they can tell you what is it about this that excites them, other than just building the company and growing the share price. And the definition of the right people in the right seats constantly changes as the company grows and challenges evolve. So it's important to bring team members and advisors on who understand going in that they may not be the right person in the right seat in a couple of years. And even then, that person's focus has to be to do what is best for the company and move out of the seat when the time comes, including yourself as the founders and CEOs. And then choosing the right financing mechanism is the lesson 8 I have. It's very hard in the entrepreneurship world in America to really remember that external finance from equity investors is a tool on the journey to build a company. It is not an end in itself. There's too much press, there's too many magazines that want to do profiles about you for raising money and so on. It is all just noise, and early noise in advanced materials really gets in the way because you cannot deliver it as fast as software code. It just is not possible in my mind. So raising lots of equity investment by marketing what your innovation is well before it is ready for big time does not necessarily speed up the materials commercialization. Why? Because the bottleneck is way at the end of the market. What is the market adoption rate determines if you have a successful combination of end use application and all other technology. So my recommendation is start with federal R&D grants. Really figure out what is that minimum viable revenue capacity that you can build where you can run a 5, 6, 7-person company, right? And go raise money from investors who understand material commercialization. How long does it take? Which business models work? And who also have specific goals in the industry. People might say, I only want to invest in the solar energy industry. I only want to solve plastics recycling problem. I'm okay with accepting lower returns as long as the problem gets solved. And there are people like that. It's hard work to find them, but it is better to find these long haul investors than going after the very next fund from a Silicon Valley investor, for example. And then focusing on earning profitable revenue from end customers to reduce investment risk is what, as founders and academic supporters of entrepreneurs, we should always stay focused on. And what that means internally in the companies, your R&D efforts should all be focused only on profitable revenue. The trouble with advanced materials that I found is it's very easy to start new R&D initiatives because everything looks like it's an application, right? And too many R&D projects get started and not enough focus exists. All R&D spending should be focused primarily to reach cash flow break even so the company can stand on its own 2 feet. So now what I'm doing is we've started this new company, Professor Kumar and I co-founded it. We're implementing these lessons focused only on recycled PET commercialization for the microcellular PET. And we're collaborating with a dedicated team of commercialization experts to really drive this widespread use. So that's the end of my talk, and I'll take some questions.
Excellent. Thank you so much. I think we all can give you the quiet virtual applause with our reactions.
Okay.
But now it's time for our Q&A. So if you guys have questions, feel free to use the raise hand feature under participants, or you can ask it in the chat, and we can also field it there. Just to kind of kick things off, I got 2 questions. One's a mechanics question, and the other one's an entrepreneur question for you. Which one would you like?
Mechanics first, see if I remember some.
It was really interesting, the transition you talked about from sort of like the slabs to the thermal formed cups. And I think you kind of talked a little bit about how, it was like the 50% reduction kind of dropped to like a 40%, I think it was, in the thermal forming. I was just curious about, could some of that be from just like how does this material or this process handle when it gets thermally formed? Is it, are the corners kind of condensed back again a little bit, and loss of the microcellular?
Yeah, so what happens, Nate, is that in this kind of a forming technique, the wall thickness from top to bottom is exactly the same because there is no stretching due to tension, right, in this kind of a forming technique. Whereas what you find in thermoforming is you have to start with a process where the material is, say, 1.8 millimeters thick at this point in order to achieve 0.5 millimeter thick at the bottom of the cup. And that basically is the challenge. So as a result, what ends up happening is the cup is completely over designed at the top, right here, right? It's way too thick at the top, and it's in order to get to the right thickness at the bottom. So that's kind of the difference on why you don't see all the reduction in weight.
Thank you. I'm just checking the chat for any additional questions. I'll turn off the, people can unmute themselves if they want to also ask a question. My next question though is, are you going to write a book? I think these 8 lessons are fantastic. It's like 8 chapters right there of your book.
Yeah, so Professor Kumar and I have been approached by Wiley Science for a while now, asking us to write a book. And we have a technical writer who is our partner in this company for a long time, Shirley Lee. The 3 of us constantly talk about waking up in the morning and spending the first 3 hours writing the book, but we haven't gotten around to doing it.
Along that same idea, I know you kind of talked a little bit about, choosing the right moment, getting the right partners, and, things don't always go with the, you have your best intentions and sometimes there's hiccups along the way. And I was just kind of curious maybe can you reflect a little bit about, this idea of spinning out, but should there be better ways of sort of spinning back in to kind of regroup and this process of entrepreneurship seems to almost be a little bit of a one-way door where the technologies and ideas leave, but the university could have a symbiotic relationship where there is some coming back into the fold to get stronger.
So what I found it is, and this is where Professor Kumar and my combination has really worked well, is we, at least in the companies I formed and run, we absolutely have no problem in discussing every idea we have with the students and Professor Kumar in the lab, because the tension is not that I want to own all improvement IP and reduce the amount of payments to the university. Our goal is to get the best solution and keep the payments to the university going on way into the future. Right. So actually building that graduate student and professor relationship and graduate students spinning out, there is an ability to do this. What I typically found is when just very large companies come take a license, they want to take the license and just completely go quiet. They don't share any information and so on, which doesn't really solve their problems fast enough, because then there is the not invented here syndrome that sets in. I really think spin out should ideally have some PhDs or some master's students from the technology in the company as founders.
Great. We've got 3 questions, one from Deborah, Anirudh, and then Elizabeth. How about we just go in order with Deborah first? If you'd like to unmute yourself, if you want to ask your question.
Sure.
Yeah.
Yes. I'm in marketing at Commotion, and I'm just curious to know what programs in particular over all these years that you used through Commotion. Did you get a gap fund? Did you go through the idea to plan workshops, I-Core, etc.? And then also secondary, what advice would you give to others in working with Commotion?
Hi, Deborah. Thanks for that question. At Commotion, before Commotion was Commotion, I was We worked with the tech transfer office at that time. I kind of cut my teeth back in 2002 to 2003 when the business plan competition was new and so on, and had the help of business school professors with the help of tech transfer office, Professor Suresh Kotha, John Castle, and so on. Again, the help was really mentorship one-on-one. In advanced materials, I just don't see how you could go through a standard 5, 6, 7 week process to build it, because it is just a very slow process to build it out. So I think any mentorship program with the university co-motion office can bring advanced materials entrepreneurs or these large company retirees to come become a part of the ecosystem would really help. And I think really that mentorship happens over 2-3 years. I've been helping a few companies, and I've seen it took me 3 years to really share the lessons I had to give them so they could use it and make a difference. So I would really have like a mentorship program, if you will, specifically for these advanced materials companies. That's what they need. The next question I see is from Anirudh. He's asking, is there a particular reason to stick with PET? Anirudh, that's a great question. There is no particular reason to stick with PET other than what is a big market in which we could make an impact. High performance polymers like PEI, polyimide also can be processed with this technology. The real challenge is what is the market size at which investors are willing to invest. So the real, because you have to eventually, once you realize that there is a process innovation and an equipment innovation that has to happen, the investment sizes are too big, and people don't invest unless the markets you go after to disrupt are big enough. If the innovation was only material composition and everything else stayed the same, the machines, the process was largely what the industry uses, then starting off with the bootstrapping approach where, for example, I have a job in the daytime and I do something in my garage at night, that would work in that case. So that is a real challenge. In this innovation, the problem is we are doing material composition, process, and equipment innovation. That's why it's very important to define what you need to do before you choose the right application.
I see. Thank you so much, Krishna. Thanks.
Okay. Elizabeth, you have a question?
Hi, yes, great talk. Thank you. I loved it. I liked how direct you were and honest, and I appreciate you just being candid with us. So my question has to do with, since a lot of your work is process based, can you speak to the extent that basic science research played into your process, not only innovation, but optimization? And then also I assume there are controls in place, temperature or pressure or, time for this process to go through that you can vary along. And can you speak to how maybe you did just do a parametric study to see what was optimized, or how did you feed back into your basic science and PhD research?
Yeah, so what I found in the basic science and so on, Elizabeth, is take, for example, a pressure vessel and a valve for a pressure vessel. Doing it with a 1/4-inch valve in Professor Kumar's lab, the parametric study works very well. But once you go into 1-inch valves and 2-inch valves, and the valves are stuck in the middle of temperature fluctuations in the scale-up world, very quickly you'll find that everything you did at a PhD and a science level is not very easily translatable. I was lucky that my first investor was a controls guru. I was unlucky that he was not in my face enough, right? He was a more gentle soul. And he was right there telling me where the problem was. And because he didn't have the loudest horn, it was very hard to kind of separate the noise from the quiet people, if you will. So I would say it's hard, one, it is hard to remember academic lessons like Professor Kumar taught on axiomatic design. Don't do coupling. It's very hard to remember at the velocity you're going when you have tens of millions of dollars that you have to spend and grow a company. And the second thing is, it's typically in the quiet engineers, mostly the quiet retired engineers who want to help you, is where many of the answers lie. It's really up to you as the young entrepreneur to slow down and listen and not let the noise kind of carry over. And I did that, and Larry is still with me. He's still a part of our company. but I'm now listening better to him. That's what I would say.
Awesome. Thank you.
Eli has a question. What are some things that you think you had learned elsewhere and were able to apply here with good success? Eli, I learned elsewhere that you should always try to hire people you have no problem working for. When you do that, tons of your problems very quickly are solved because you're not constantly watching your back. And it's very hard to not watch your back in a high velocity startup. And the trouble is that's what the startup needs is you should focus on the startup success and hire people who are absolutely better than you. And it really helps solving some of the really tough challenges, especially if the challenges last 7 years, 10 years or so on. So many of the people that I'm building the company with in Vesicus right now have been there, done that, have seen the dark side at a much more depth than I have, and they're willing to share the lessons. And I think that's one lesson I learned in some management book about hiring better people than myself as an engineer, and I never regretted it. Just don't try to be the best in the room. That'll happen when you are, anyways. Okay.
Krishna, this is John Kramlich. I just had a real quick question. And I really enjoyed your talk. That was super. So it seems like there's an alternate funding model depending on the technology where basically you go all in and you try to get market penetration as fast as you can against competitors. And the idea is either get big in a hurry or die. And I wonder, do you ever see any, your alternative was to basically kind of grow the company in a match pace with the technology and the growth matching the demand as you go. And do you see any place where that alternate idea of growing quickly to get market share in a hurry fits in this area at all?
I just don't see it, Professor Kramlich. I think in advanced materials, what you'll find is even though they take a long time, when you get to the end of a 10, 15-year period, those materials are going to stay in the economy for at least 50 years, close to 100 years. PVC pipe was introduced in India just as I was leaving the country in 2000, right? And even now, it is the only solution that is around the world, and it was introduced in America in the 1950s. So I think as long as you're willing to take a couple of shots in a 40, 45-year career, advanced materials will lead to financial success, reputational success, and so on. I just think the right way to build advanced materials is slowly, deliberately, so investors make money, you spend less money, keep the company small, don't go to 163 people without knowing what the market penetration rates are, and so on. And I think it's a much more proper way in my mind to build a company. Just throwing money at it is not going to solve it.
Okay, good. Thank you.
Thank you, everybody, for coming to today's seminar. I guess give Krishna another round of applause.
Thank you.
And I think if you want to stick around a little bit later, that's great too as well. But thank you very much.
Okay.